Okay, so to give you a little backstory, if you were to do this subject in past years, in the labs, what you would do once you complete your Verilog code is that you need some method of testing to see if the device works. Now, we never used to use simulation. What we used to do was configure the board with your NEOS setup, and then run monitor program, and then run some assembly code that would go through and try to access that slave device by running those instructions. And that's how you test it. So to test it fully, you need to test all the different operations that your slave device should work for. So you should test storing bytes, storing half words. Words for now we can ignore. But yeah, so storing bytes and half words, storing to different addresses. So you have 4 registers in the slave peripheral device. So you want to test writing to each of those different registers and doing a store byte and a store half word to each of those registers. For the byte transfers, you also want to check that you can store to an even byte address and to an odd byte address, and that would test your byte enable functionality. So these are the kinds of things that we were aiming to test if you were doing the on-campus lab. Now, because we can't do that, we test the functionality of your Verilog module using simulation. So running the test bench, and that test bench, given the file that I've provided, will provide a range of inputs to the module, and it will also contain the expected values based on those inputs. And then it compares the inputs given and the outputs generated by your Verilog module to see that it's correct. Now, because you can't actually run the assembly code on the board, we are just looking to see that you understand how you would have done that. So you could do that using the simulator, and assuming that the memory access replaces the access to the actual slave device. So I'm going to share my screen. Before I do that though. Okay, so on the online simulator, if you go to it and make sure that you select NEOS 2 and NEOS 2D2, this gives you a virtual version of a D2 board that has been configured to work along with a bunch of peripheral devices that have been already assigned. So everything that you see on the right-hand side here, you have LEDs. These are in place of the red LEDs on the board, and they are assigned to the base address, whatever this is, 1 and 7 zeros. The next one was what the green LEDs would have been. That's assigned to this base address. Okay, so these addresses are all memory mapped. So they're all assigned an address range that is the maximum address range that the processor could access on that bus. Because it is a 32-bit processor, it has a 32-bit address space. And that address space can either be given to memory devices or just given to devices connected to that shared bus. Sorry, there's a chat. So we are writing the assembly code for 7 segment or to make connection between the NEOS and peripheral device. This is the assembly code that will be run or would have been run on the NEOS processor to access the peripheral device. The 7 segment is just an external module that exists only in Verilog to directly connect to the peripheral device, not via a bus, just direct connections to be able to view what's stored in the peripheral 4 registers. So just ignore that for now. Getting back to this. So in this particular simulator, it has one device that is a memory device, and it's 16 megabytes. So whatever range of addresses that would require, that's what it is assigned to. And it just happens to be starting at address 0. So from address 0 all the way up to whatever a 16 megabyte address would be, that is assigned to this particular memory address. And then all the other peripherals have a larger base address, as you can see. Switches are at this, push buttons. Okay, so what you can do is you can write code here that will access the memory in place of your slave peripheral device. So in your setup in the lab, I believe your address values will be in the range 0 to 0x7ff, 4fs. That is the address range for the Avalon external bus bridge. Now, your slave peripheral device is connected to that bus, and you have only 4 registers in there. So we've chosen the decoding. If we go back to Quartus, let me try and scroll without giving away all the answers. Actually, I went through this in the lecture, it's fine. So we are using the top 2 address bits to decode the address. That would mean that each register, for example, register 0, would get a quarter of the whole 19-bit address space. So that would mean reg 0 in the slave device would have a range from 0x0 to 0x a quarter of 80,000, because this inclusive of those 2 would be 80,000 addresses. So this would be 1FFF. And the next register would have an address that starts at 0x20,000. And it goes all the way up to the next quarter, which is 3FF. Okay, so those are the memory mapped addresses. So if we are replacing the slave device with the memory here, you can search to those addresses. So 0 would just be there. You can go to 0x20,000, and there would be some location here. Okay, so to write to that, you need to do a store operation. So let's do a store byte. Before we do that, we need to save the address that we're going to write to. So let's write to address 0 for now. So we will use move immediate address, and into R2, we will store the value 0x0. And then that is the address. Oops. So don't confuse these registers that I'm putting here with the processor registers. The processor registers are here, and they are within the NEOS processor. When I do this underscore, I'm referring to the slave device registers. So that stores the address. Then you want to store a value that you're going to write into there. So we'll use R3 to store the value. And let's just write FF. Okay, so to write to a memory map device or to a memory device, you need to use a store operation instruction. So we do store byte. We take the value in R3 and we store it to the memory address pointed to by R2. Okay, and if I was to explain this in some pseudocode, it would be memory R2 plus the offset 0. So this is the offset here. So that memory location would equal the value in R3, the processor register, which happens to be FF. So just to run this one instruction or set of instructions, we'll compile and load. We will step over to do one at a time. So the first two, where did that save? Oh, I pressed the wrong one, I think. Let's restart. Yep. Why didn't it save? Let's go back to editor. What did I do wrong? Let's choose R5 instead. Okay, that's better. All right, let's go back a bit. Something went wrong. I don't know what it was. Yep. Okay, so we first load the address, then we will load value 0xff. Then we will store byte, was it? Maybe it was because I was using store byte IO. Okay, so starting that again, the first two instructions. Oh God, it's happening again. Oh wait, no. Never mind. I was being a bit stupid. It was storing 0, which was correct. It just wasn't showing the red pop up. Anyway, first two instructions store 0, which is the address into R5. The next instructions store FF into R3. And now the store byte, what it's going to do is take the value in R3, FF, and put it into the memory address 0. So if we step over that, and now we go into the memory address and we go to 0, you should see that the first byte is FF. Okay, and then what we can do is we can read that back with a load byte. Let's store it into R7 this time. And then the address still goes on the right-hand side, which is R5. So for a load byte, what it's going to do is going to take the value in memory defined by this side and store it, load it into R7, which will be here. Run that again. Step over. And then now when we step over the load byte, it will read it back. Now, the issue that you see here, it's actually loaded all Fs, is because the load byte does sign extension. So it loaded in the value FF, but that as a byte, a signed byte is actually negative. So it does a sign extension and fills the rest of the values on the left with ones. That's why you see Fs. So if I was to go back and change the value that I was storing to, let's say 33 instead. So the leftmost bit is a 0, which makes it a positive number. It now loads 33, and the rest is zeros. There's probably an unsigned version of this as well, which will fix that issue. Now, that code is writing to the address value 0, which is assigned to register 0, slave register 0. Now, if we wanted to write to slave register 1, we need to choose something within the range 20,000 to 3 FFFF. So once again, now we can do maybe a store half word. So we can do put a value into R4. This is the value that we're going to be, the address value. So we can just choose 20,000. And then store a half word, so that might be 1, 2, 3, 4. Now we're going to do R6 to address R4. So as we step over, that's the first. Okay, so now it's loaded address 20,000 into R4. Stored the half word 1, 2, 3, 4 in R6. And when we do the store half word, it should have stored into 20,000 in memory. So we go here, 20,000, and at 20,000 you see that 1, 2, 3, 4 is in the memory location. So we can then load that back out, load half word. And this load will load the value out here. So that's the kinds of tests that you want to be doing. To test out the different locations that map to the different registers. But you need to make sure that you try all the different types of instructions, so store byte, store half word, and then load byte, load half word, test different addresses to make sure that each register is accessed, and also check the odd and even byte values. Are there any questions? I kind of haphazardly explained that with issues. Can I make a summary? Sure. Before I go through with the summary, are there any other specific questions? No, really? Okay. Yeah, so the simulator is meant to be used purely to practice your assembly code and to write the instructions that you would have been using to test your slave device if you were to do the on-campus lab. So to do that, you'd need to be doing store and load instructions to some memory mapped address. So in this case, you can assume that the slave device is one of the memory locations here, because this memory, which is 16 megabytes, is currently mapped to the address space starting from 0. So you would put in some certain addresses into registers that you'll be used to point to the memory mapped addresses. Those registers will need to be within the range that are mapped to your slave registers. So there are 4 slave registers. Each of them is getting a quarter of the address space. So if the address space is from 0 to 7FFF, that equals 80,000 addresses. Therefore, 1/4 equals 20,000 each. Okay, so you would need to choose a range, an address within each of the ranges that is mapped to each register. You store that address in a register, you store a value in another register that you want to put into that slave register. You do a store byte or half word to that address, and then you do a load byte or half word back into a processor register to test the value. And then you want to also check maybe some other addresses and offsets that would result in an odd address. So if I was to give you an example of doing a store byte to an odd address, you can put an offset of 1 here. And if we step over that, when we do the store byte at memory address 0, you should see that 33 got stored in this second byte, which is digits 3 and 4 there. And then we go back to here and we step over, we should find that it loads it back into R7 as 33. You want to check all the corner cases, so you might want to check address 0x1FFF, writing and reading from that, and then check the one that should be mapped to the next register, slave register, which is 0x20,000, and do the same for maybe 0x3FFF and 40,000 and so on. Is that a good enough summary for you, Indy? Any other questions? Move immediate address R3, can I explain? What about it don't you get? What it's doing? It is just storing the value 0x33 into processor register R3, which is here. That is the value that we're going to be writing to the memory address with the store byte. Store byte will take the value in R3 here, and put it into the memory address pointed to by R5 plus that offset. So R5 contains 0, so 0 plus 1. In memory address 1, it will store the value 33. R3 is a processor register. So these processor registers exist within the NEOS processor. The slave registers are outside of the NEOS processor. So I don't know if you saw the diagram that I had before. Let's see if I can draw on here. Okay, so this is your NEOS processor. The registers are in here, R1, R2, R3, all the way down to R31. They exist in the processor. Then there will be this bus, which talks to your slave peripheral. Okay, in that slave peripheral module, in your Verilog, you have 4 registers. So this will be reg 0, reg 1, reg 2, reg 3. Okay, they're different things. These registers here let's go. These my pen has stopped working anyway. These registers here, because they are in the slave peripheral, are mapped to memory addresses or memory mapped addresses. Does that make sense? Thank you. Are there any further questions? I feel like we're spending a lot of time on just understanding one assembly instruction. Okay, if no one has any other questions, then we can go back to the main breakout room. I mean, the main Zoom room. So this is your last chance to ask any questions about the assembly stuff. Okay, just a little bit of advice. If I don't get any feedback from you when I'm explaining this stuff, it's hard to understand whether you get what I'm saying or if I've gone through too quickly or missed things. So please try and engage. Yeah, that would help a lot. Okay, so we've got question. We have to store the address in any one of the 4 registers. Yeah, not, and you have to test all of them. So you have 4 slave registers. You need to test that each of them or accesses to each of them works. So you would need to store to an address in the range of what's assigned to register 0, slave register 0, an address that's in the range for slave register 1, and then 2, and then 3 and 4. Or 0, 1, 2, 3. Amongst doing the other tests as well, so testing the different types of transactions. Does that answer your question? So are we adding 4 registers to processor register? Not really, no. Don't think of them as registers. I think that's confusing a lot of people. They are slave devices. It's like memory locations on a slave device. Think of it like that. We are adding a device to the bus that the processor is on. The processor is a master on that bus, which is the Avalon bus, and there are multiple slaves on that. One of them is on-chip memory, which stores the processor's instructions. One of them is the external bus bridge. That component, that slave component, connects the actual Avalon bus signals out to the peripheral on external bus module, which is a slave device. And the processor can access that slave device through the Avalon bus by doing certain instructions. And in that slave device, there are 4 locations, each location holding 16 bits that you can access. You can either store to or load from. Okay, next question. For moving the address, we can use any register other than 4 registers, but storing, we should only use the 4 registers. Yes, I think if I understand your question correctly, these registers in the processor, you can use any of these to put values into. Those values can either be addresses, or they can be the values that you're trying to store into the slave device. And when you store, you take that value and you put it into a certain address in the memory, and that memory maps to the slave device and a particular slave register location. Yeah, so I just chose arbitrary processor registers in the code here to load into or to store from, to store the address. So these are all general purpose registers in the processor that you can use to put values into and to do operations with. Okay. For the people that are asking these kinds of questions, you might want to go and learn about RISC processors, so reduced instruction processors, instruction set processors. So maybe look at MIPS. If you can't find enough NEOS documentation out there, look at the MIPS processor. The MIPS RISC processor is very similar in terms of its assembly instructions to how the NEOS processor works. Go learn a bit more about that, because that is prerequisite knowledge, and that will help you with these kinds of issues, because I think that's where the gaps are in your knowledge. Any other questions? Okay, it's gone pretty quiet. I'm going to assume that no one else has any questions unless I see a post in the next 10 seconds. I'm going to leave the breakout room then, and everyone can do the same. That's all right. Hopefully it was clear. It was kind of all over the place, but I wasn't quite sure where everyone is at in terms of understanding, so I tried to go into more detail than I probably needed to. We can all go back to the main room, and then maybe Aaron will have some more things to go through. Well, he's probably already gone through, I guess.